And the topic for today's session is called imaging in short. I'm not absolutely sure this is proper term in English. You may find definition of imaging by yourself, but I hope everybody understands what it is about. And before we go into imaging itself, here is some reminder from your secondary school physics, because before we start talking about images, we need to talk about what is light. And there is general consensus that light is electromagnetic wave and or particle. So this means it has either electric or magnetic properties and also either wave or particle properties. And general rule here is that as longer this wave is, as more it behaves like a wave, and as shorter this wave is, as more it behaves like a particle. And I touched it a little bit when I talked about radio waves for data transmission networks, because properties of light influences how can you implement and how can you use radio waves for Wi-Fi network. And what is important is that electromagnetic waves or light in general can go through vacuum. It doesn't need any media to propagate through, and depending on length of this wave, and this means it is inverse proportional to its frequency, you may call them either radio waves, microwaves, infrared light, visible light, ultraviolet light, X and gamma rays. And here, even in names, you can see how these properties of light changes from the waves, because when we talk about radio and microwave, we talk about waves because that's how light behaves in this region. But when we talk about X and gamma rays, we talk about rays. So here light is behaving like small and strong particles. And speed of light in vacuum is about 300,000 kilometers per second. And that looks a little bit strange to me, because if you know C prefixes like kilo, mega, giga, tera, peta, exa, zeta, iota, and in other direction milli, micro, nano, pico, femto, opto, zepto, yocto, then of course these are 300 megameters per second. But when I, for example, say that I have driven with my car, or actually not I, but my car has driven 100, let's say, or megameters in its life, most of humans do not understand what I'm saying. And wavelengths of 1 gigahertz frequency, why 1 gigahertz is very important, because around that range you have clock frequency for your computers, around that range you have clock frequency and radio wave frequency for your home routers. So this 1 gigahertz of frequency is about 30 centimeters in length in air or vacuum, and it takes 1 nanosecond to travel. And visible light is part of all these possible different frequencies and lengths of electromagnetic radiation, and it looks like this. So here this scale is logarithmic, so you see here that from this part to that part is increasing frequency, and here is decreasing length of waves. So these are hertz or cycles per second, and these are meters. And so it starts with very long waves, very low frequencies like radio waves, then microwaves, infrared waves, and also infrared light, then visible light, then ultraviolet, X-rays and gamma rays. And particularly for light, this range, what is considered light, is, if you talk about wavelengths, is approximately 100 nanometers starting with blue to 700 nanometers with red, so what you can see here, or 400 terahertz with red light till to 700 terahertz for blue light. And here are rainbow colors or spectrum of visible light, how it looks like for our eyes. And so here it starts with blackness because we don't see ultraviolet light, then we see something very violet, then blue, green, yellow, orange, red, and then it goes to blackness again because we don't see infrared light. But our face, for example, is very good at receiving infrared light, especially our lips. And when different kind of color scales are introduced, because here it starts with black and here it ends with black and opposite vice versa, this linear bar actually may be put together as a circle, and then you get this circle of colors schemas for different kind of theories. And visible light is this part of electromagnetic waves or spectrum what we can receive with our eyes. And if every color is more or less equal presented in this spectrum, altogether we perceive it as a white. And if we do not receive anything, then we consider it as blackness. And of course, black is actually not real color. Black actually means there is no light. And what is important is that we have two different kind of visual receptors in our eyes, rods and cones. And rods are higher resolution in terms of angular size, but they are sensitive only to intensity of the light, and cones are not so good at angular resolution, but they can sense different kind of colors as well. And what kind of colors we can see? In general, we can see red, green and blue colors with these cones. And if you put it on linear scale for different wavelengths, we see that there is no very big difference between red and green. It is a little bit bigger difference for blue color. And here what is important is that not all people, not all humans see light in the same quality, in the same details, because there are still some small minority, like 8% of males, who do not have two different cones for red and green color, so they are daltonics. They have only one type of cones. I do not know which one, either red or green one, but so these two little bit different ones are actually just one. But quite large part of females actually have two different cones to see green light. Usual approximation is that humans see three different colors, but actually quite a lot of humans see 4 kinds of different colors. So many women actually have 2 different types to distinguish between green color and another green color. And that's one of the reasons, for example, why females are much more careful about particular color, because they just see it a little bit better. And then there is some very small minority of people who do not have blue cones, so they perceive only either 2 different kind of red and green, or 3 different kind, I don't know, red, green and another type of green. And it is not confirmed by peer-reviewed materials, but I have read in internet that one woman claimed that she can actually see different shades of or types of blue color with different cones. Something like she sees a little bit better ultraviolet light than most of humans. But these are just unconfirmed stories in internet. I can't be sure about that. So that's how we... And then of course, in difference with octopuses, and we mix these colors together to see all other shades of light. And for example, we can have the same perceived color getting different kind of colors in actual reality. So here is approximate schema how we can distinguish 3 different colors. And if we have one particular monochromatic color filtered out with these wavelengths, it actually makes approximately the same feeling of green than, for example, mix of the similar amount of red and similar amount of blue colors. Because what is important here is what kind of feeling or intensity we get for this particular cone. And because these things overlap to it, probably I think it's more proper way to describe would be following. So we can get the same feeling of light either with lower intensity poor green color, or with higher intensity of red and blue color, because amount of intensity what we get here as a feeling will be the same, because these things overlap. Of course, if it's actually red and blue, we will feel also red and blue as well, but because what we actually register here is total amount of different kind of feelings for this, there may be that we can get the same perceived color mixing different colors together. And what is actually white light? White light is actually green light, because if we look on how different kind of hot bodies radiate different kind of colors, then there is equation and theory behind that. But what happens is that hot bodies radiate this exponentially increasing and exponentially decreasing amount of different kind of electromagnetic waves. And the peak here depends on how hot this body is. And if we look on star like Sun, we see that peak color for it is around green color, but of course it emits little bit of light till to blue and violet part, and of course some part till to yellow and green part here. And if somebody emits light with such intensity that peak amount is here at green color, and then it decreases going to violet direction and into red direction, we think that this is actually white light, not green light. But if this body is hotter, then its peak of color is somewhere in blue part. We consider such hot body like a blue star. And if it's cooler, then peak here is around red color, then we see it as a red star. But we don't see red stars around us in night because all green stars, with our perception, are actually considered white stars. So that's one thing. And because of this perceived value of different mixes of colors, we can put almost any color with some kind of precision by mixing only 3 different colors for these colors which are chosen in 2 different ways. If we use additive mixing, like for emitting devices like displays, then we start with blackness, and then we add more and more different kind of colors to this blackness. Then we are using RGB scheme from red, green and blue, so all these 3 components correspond to approximate peak value for these 3 different cones or 4 different cones. So this approximation may not work so well for some of humans, mostly females, because they see a little bit more different colors than just 3 different components. And then you put them together, and blue together with red is cyan, and green together with blue is this is magenta, this is cyan, and this is yellow, and all together are white. But if we start with reflected light, like we start with white paper, and then we subtract some parts of colors, so some parts of colors are absorbed, then to get everything black we can use 3 good and ideal colors which are opposite of our cones. So if we look here on these 3 different peak values for our perceived colors, so if we subtract it, we need to remove we need to absorb everything besides blue, and everything besides blue is this yellow part. So if we remove or absorb green color and red color, what is remaining, what is reflected from paper is blue. If we want to see just green color reflected, too many undos, then we need to remove or subtract this part of color and that part of color to have only remaining red part. So this would be absorbed and that would be absorbed. Or vice versa, if we want to show only red part remaining, we need to absorb blue part and green part, and then we'll have only red part. So for such subtractive mixing, which is used for printed materials, that you start with white background and then remove more and more colors from this white part, then we use mix of, for example, red and green. What perceived value here would be cyan, magenta and yellow. And because these three colors are not ideal, usually we add fourth color called contrast. For some reason it's K, not C, which is actually black, because mixing these three together doesn't show you black with good contrast, because these are not ideal colors. Some of cyan or magenta or yellow part of colors are still reflected back from the paper. And because of that, if we are dealing with displays and emitting devices like light diodes, etc., for these basic colors, red, green and blue schemes are used. If we use reflected light, so here we add more and more light to the blackness, and here we remove more and more light from the whiteness. We use a remaining part of colors, perceived values of which are cyan, magenta and yellow. And then what is very important is that as an optical device, our eyes are not very ideal. We see with high resolution only in very narrow field in center of this field of sight. Let's say just only a few small angle here, and then everything else is perceived much worse in both in resolution and in color perception. And what our brain does is that when we are looking, for example, pay attention to this picture here and look at the center of it, you see that it is like pink circle with white and dark semicircles around it. But when you move slowly your eyes around it, it looks like it is waving like waves, and this is artifact of our brain filling empty spaces, what we actually do not see with our eyes, just by filling up blanks. Similarly, in this picture, if you pay attention to any dot here in between lines, you see that these are actually white dots. But if you look on one particular dot particularly and then try to resolve what kind of color are these dots, here, depending on your attention span, they are mixing between white and black dots. And again, why it's happening, it's because if we do not pay attention to the center of line, we actually don't see these details precisely enough. And our brain just fills up this pattern as much as it can understand this pattern. And it worked pretty well when we are living in woods and savanna. But when we can create these kind of artificial images, then of course we can show that filling these gaps is not very good. And here is another thing, that if you pay attention here and do not imagine it as a 3D image put into 2D images, you see here that it is just one plain rectangle which is put here together. But if you look on it just briefly, and there's theory called theory of carpented world, and what this theory says that because while we are living in civilization, in cities and houses around desks, etc., what he have learned is that every angle which looks not straight angle actually is straight angle, but is skewed because of our perception and perspective. So, and because of that, we may see here a conflicting picture how exactly these two parts are put together. Of course, in general, it is just plain lines put together, but our perceived imagination, when it fills these poorly visible gaps together, it works pretty badly. And last picture here is very important. We will talk about CECAs for this when we talk about video imaging and mixing. Here is a moving picture which changes numbers precisely after 1 second, and to see how your brain is filling up invisible gaps is you should look somewhere in different place. For example, pay your attention and look somewhere here, and then move your eyes and look on this picture and count these seconds. 1, 2, 3, 4, 1, or 8, 9, 10. 1, 2, 3. So count this as a regular sequence, but when you will look on this picture, suddenly moving your eyes, you will see that some of these seconds are a little bit longer than other seconds. Why it's happening? Because when you are moving your eyes, which are pretty soft and mushy, they are actually wobbling around, and you can't see anything clearly while your eyes are still wobbling like water, like liquid. And what is happening is that during this time, while your eyes are still wobbling, our brains actually are ignoring these blurry images, but they show to our sense or consciousness only these images which are seeable, you can see clearly, and then it actually fakes your past and says that you saw this particular number of seconds all the time, including that time when you saw blurry image. So to describe it more clearly, so here is time axis and here are precise seconds. And if you move to this picture in this particular second and here it's blurry, because your eyes are still wobbling, this part of time is ignored. And then, when our eyes are not wobbling around, we see next second, like here is 6 and here is 7. And then our graphical processor memory says that all the time what we were seeing here was precise 7, not blurry 6. And so this second, which you see clearly and precisely, is actually feels longer than other things. Why it's important? Because, for example, you drive car, and if you just move your eyes very shortly to look on sides, for example, side mirror or other thing, and again, if you will not pay enough attention and you will have blurry view here, what will actually happen is that if there is some other car or cyclist which is blurry, your graphical coprocessor in your brain will tell to your consciousness, so your subconsciousness will tell to consciousness there is nothing here. Even though there was blurry bicycle or blurry child running or blurry car or whatever. And then, of course, when some collision happens, you say, oh, this car suddenly jumped in front of me. No, it didn't jump suddenly. What was happening is that this blurry image was actually filtered out from your consciousness, and then it was faked with perfect pass when there was nothing here before particular collision. So that's about this image, and it also may be important while we will talking about mixing audio and video together into movies. And then of course there are many other software glitches, but these are the most important ones. Now about imaging itself. Considering that our brain is good enough to analyze what we are actually seeing with our eyes are like not very good quality, but also not very bad quality of cameras. So if you put a small hole in box, then it will show a reverted image here on the background, only it will be very low contrast and very weak, because you are spreading out all entire image only from this very small hole. But if you add lens here, then this area of hole may be a little bit better, and here we can describe light just as a particles going. So if it is small hole, then we don't need any lens at all, and what we see here is reflected here. But if this hole becomes bigger, then this image of course will be blurry, because this light will be coming at the angle. But if you add lens here and you focus this light coming together, you may have much bigger hole here and still have sharp enough image. And that's how our eyes and how cameras work. So we put different kind of lenses here to get better sensitivity, so we collect more light, but this image is still not blurry. And of course we start with analog cameras, which were collecting this light on photo films, then these were deployed, but today we mostly use digital cameras. And yeah, before that, when we talk about view of field for different kind of objectives, usually when we talk about wide angle, narrow angle, etc., they are still compared to 35mm objectives, because it was very common to have 35mm of these films which we are using in cameras, and the 35mm of objective is 45 degrees of angle, because what it does is following that here is your lens and here is your 35mm of film, and then if you also have 35mm, not 45, 35mm of focal length, then this is approximately standard standard field. And if it's longer, then it's teleobjective, because you can zoom it in larger, and if it's shorter, then it's wide field, because it focuses light in much wider angle. And even though today this area where this light is collected is much smaller, usually they are still talking about analog of 35mm field value for different kind of objectives. And so how these digital cameras work, they have light sensitive electronics here. There may be two different types. One is called charged couple device, which is very good for resolution and for sensitivity, but it is slower, and it's mostly used for astronomical instruments, and it's just monochrome. If you want to get different colors out of it, you have to put different kind of filters of light before it to see it in different colors, and that again what they are using for astronomical instruments like telescopes, etc. But for a standard equipment like phones and photo cameras, usually we are using SMOS sensor, where SMOS means complementary metal oxide semiconductor. And what is good is that they have added filter to filter out particular wavelengths directly into this matrix of these elements, so you can see all colors at once. Only problem is that they are not so sensitive. Their range of values is a little bit smaller, but for non-scientific instruments these particular matrices are much more useful. And today these matrices are very small, usually approximately 5 by 5 millimeters, maybe even smaller. And then what is happening is that you, with your hardware and software, you read each particular value for this matrix, and you do the same analog to digital conversion as you do for sound. For each of these matrix elements there may be different kind of values, and you approximate them with one particular digital number, binary number of its particular value. And if you have some analog image which in theory has precision till to infinity, what you are actually seeing is that you are calculating particular value for particular area of this matrix, what you have received from this actual image. And then you assign one particular value for one of these cells inside your matrix, and you get some approximation of actual picture what was projected through the lens to this matrix, which, if this total resolution is good approximation to actual image. And what is important here is that you start with picture resolution. This is in old times this was the most important factor for different kind of cameras, because the resolution was low. But today, when miniaturization is still going on, also for these light sensitive matrices, picture resolution is unneeded arms race between different manufacturers, because of miniaturization, adding more and more pixels here doesn't cost too much. And because of that, at least few years ago, especially different kind of mobile phones, I don't know about professional cameras, they always talked about that previous camera had, let's say, 1 megapixel, now it is 2 megapixels, now it's 4 megapixels, etc. But what is important is that after, let's say, few megapixels, it is not important anymore. If we are talking about our eyes, then our full field of view is approximately 100 megapixels. So if we see everything from the left till to right with our eye, and here, everything is total is approximately 100 megapixels. And of course, the biggest resolution is somewhere here, let's say approximately 50 megapixels, somewhere here or here, depending on how far away you are from your display, and everything else is the remaining part. And if you are looking on some particular picture which doesn't take your entire field of view, but only some part, so picture here, you will not see any difference if it is, let's say, more than 5-10 megapixels, because your resolution of an eye is not better to see particular thing. Of course, if you look on this picture from side to the side till to the from left to right till to bottom, and then of course the maximum amount needed is approximately 100 megapixels. But if it's smaller, then starting from 5 megapixels there is no any difference at all. What is much more important there is dynamic range and noisiness, which is much harder to achieve because here miniaturization doesn't help. But because of that, usually when they are claiming that it's even better than previous one, they do not talk neither about dynamic range nor about noise, because this is much harder to improve. And then what is also very important is aspect ratio or ratio. Aspect ratio may show two different things, either aspect ratio for entire image or aspect ratio for particular pixel. Why it's important? Because usually for simple devices like cameras for your phones, etc., actual dimensions and actual size for pixels is approximately the same, so this matrix is actually consisting of squares. But when you want to get the highest possible resolution, because of these mechanical technical limits, how you can put these matrices together, they may not be actual squares, but they may be something different. Very typical it is for different kind of old video standards, because for these old video cameras, usually width of these pixels were bigger than their height. And because of that, you need to know not only number of pixels in one dimension and another, but you also need to know actual aspect ratio, which may be different than ratio between pixels, because pixels may not be squares, but they may be some kind of rectangles. And usually, how it's done, at least for video cameras, if it is happening, then width is usually bigger than height. And then aspect ratio, of course, is important, because you know that the actual resolution in one dimension is greater than in another dimension, and then if you do not know information about aspect ratio and you assume that all pixels are the same size in both directions, then you have either too wide or too narrow image, depending on in which direction this aspect ratio is actually wrong. And here is example about these different kind of pixels. So here is a little bit higher resolution, here is a little bit lower resolution, and here is even more lower resolution. And that of course decreases, quality decreases as number of pixels decreases, because we can see that this approximation is not as good as original image was. And similarly, you can, so if we look on pictures and compare them to converting sound into numbers, this pixel resolution is something like sampling rate. You may do this sampling either more frequently or less frequently, and if you do frequently enough, then you don't see any difference at all, because these samples or pixels are so many and so small that you don't see any difference. If this rating is not so high, so the sampling rate or resolution is low, then of course you see difference. And similarly, you can describe colors with bigger or less precision, assigning more precise or less precise numbers. And for example, in these pictures, actual image resolution is the same, but difference is how precisely you represent, in this case, only gray color or intensity of emitted light from the monitor or reflected light from sheet of paper. So if these numbers are longer and more precise, you see it as a better quality, but if you decrease range of assigned numbers, so here it was from 0 to 255, here is from 0 to 15, here is from 0 to 3, and here is either 0 or 1. So resolution or sampling rate is still the same, but because numbers which represents these different shades of gray in this particular case are less and less precise, then of course you now see that it is not high quality image because of resolution of color. And so resolution of color for images is the same as a resolution for value in the sound pressure. If you have bigger numbers, you have more precision to describe particular area, what its intensity is. If you have smaller numbers, then of course you can't represent all different possible values between these pixels. And when you are representing color there, then you describe it either in two different ways. In most of cases, because we are sitting on displays and at screens much more times than we are looking on reflected light like sheet of paper or electronic ink. Therefore, usually we describe everything in RGB schema, which is for emitted light, when blackness means as black as your display is, and non-black is part of red, green and blue colors, which are more and more, and everything is at maximum, it is considered some kind of white. And you can use either 8-bit for one particular color, so in total they becomes 24 bits for all three colors, or you can also use 16 bits for each particular color, then it is 1, 2, 3, 4, 5, 6, 8, 40, 42, 48 something bits for one particular pixel. And of course, if you are preparing it for printed media, you use SMIC schema, then you describe it as 4 numbers, where 3 numbers are color and 4th number is blackness, what you need to add there. And then when we do different kind of compression for images, then because our sensitivity or angular sense for intensity is smaller than for color, different kind of compression algorithms are that they describe, for example, intensity of each particular point here in grayscale for each point, but for color they, depending on different kind of compression schemas, color may be actually described only for some of these pixels. So here is intensity, here is color, intensity, color, intensity, color. So, and if this total resolution is good enough, we will not see any difference that not all pixels are actually collecting information about color, because we don't see color with the same angular resolution than we see black and white or just intensity. And again, you can find out that our resolution of color and maybe I can find out. Okay, I will find it easy. But again, our brain is filling up gaps, and if we have only few colors in some particular area, then our brain fills these gaps and it says that everything is colored in the same way, even though we can actually see, if we pay attention, that not everything is colored in this black and white image. And now about image modification, and of course here we talk about modification of digital images when they are already converted into array of colored or not colored pixels. So we take some original image, we open it in computer program, and then we can do different kind of changes into it depending in our needs. So first we acquire some image, either it's already digitalized or we digitalize some analog image using scanner or whatever. Then we represent it in different kind of file formats, then we process it, and then we may compress it and do other things. And all these different kind of processings, of course, we can mix images together, we can put image into image. But if we are working only on one particular single image, then we apply different kind of filters. And filters are analog, digital filters are analogs to old school analog filters when you put different kind of colored glasses in front of your camera. But of course, with digital filtering you can do much more than you could do with analog filtering. And there are two different kinds of these filters. Global filters, when you change entire properties of entire picture, and then there may be different kind of local filters when you select something out and you transform or change only some part of image. And probably the most widely used filter for image is like brightness and contrast control. And how does it look and why do you need? You need it because dynamic range of camera is higher than dynamic range of your display or monitor, call it whatever you like. So I hope that everybody remembers what I told you about dynamic range for sound, but so here is input value, and here is output value. And if you do not want to add some intended or unintended effects, you want that particular increase in input makes also a particular increase in output. And example, for good camera, it means that somewhere here from 0.000, from some very small till to 100 blah blah blah, some measures, you can get linear output for values also starting from 0 and finishing with, let's say, 100. So this is good dynamic range. But what may happen here is that actually, if dynamic range is not good enough, it increases, but you still register 0. So, and then when it increases, you still get better and better and better, but then when it increases more and more and more, here, so that inputs and output, it saturates, and for everything else it is just the same value. So now you have poor dynamic range, you have 0 only when it reaches, let's say, 10 here, in input here there are 10 something, and then you start reaching 0, and here starting with, let's say, 80 something, you got 100 as an output here, and that if this brightness is bigger and bigger and bigger, then you don't see any differences. So dynamic range for this camera or display now is much smaller than for that one. And what is important here is that dynamic range for cameras and these matrices of these sensors are usually better than dynamic range for displays and printed images. Why? Because dynamic range for your display is limited on how black it is when there is no light. So this blackness, when you are making photo of dark night, is much blacker than your display may actually show. And here, when you are making photo of sun or welding light or whatever, it is much brighter than your display may actually show up, because your display cannot emit so much light of as actual sun. So for monitors, limit here is how black it is. And particularly for printed images, it is limited from both ways, because you can make only as black as you can, but also whiteness, because you can't make it whiter than actual paper is. So this range is always much smaller than you can see in reality. And for example, here is a document which is made just by mobile phone. And if I would print it out on paper, then of course what was actually white here, or considered white, as actual paper would be some kind of gray here as output, because of it is not very bright in total average. And therefore, for example, when we talk about printed materials, one of the things is that if we want to have actually black letters on white paper, this range of colors and intensity should be changed. So what can we do first? We can maybe cut off what is not needed here. Oops. motion. I don't see. Kur ir iezīmēšana? Okay. Will not. So there are two different ways. You can just change contrast and brightness, something like this, until you get it more or less okay, at least for this. But my recommendation here is that particularly for GIMP, you can do it a little bit differently. There are actually intensity curves, and if it's linear, so what is an input is an output, and you can change it dynamically and say, for example, everything till to here should be black, and everything starting from here should be actually white. And then, of course, you can do, example, other things. Where are other tools? Okay, then I will show it later. So that's about this dynamic range. And then you can do different kind of color corrections, because, for example, in midday everything is much bluer than it's in morning and evening, when sunlight becomes much more reddish. So again, our brain considers that it is because early morning and late night, it auto-corrects this color automatically, but if you will print it out and you will see it in well lighted room, this picture will look wrong because of that. So you can do different kind of other changes as well. And so therefore you may do other things. And so what I showed here is that one of typical things what you need to adjust here is that you need to adjust minimum amount of color or light or darkness till to lightness in a such way that you can see it very nicely on your particular limited device. Either it is paper with printed colors on it and reflecting only some part of light, or because your monitor display is not so good, so you need to compress or stretch all these possible values what were in reality in much narrower range, which is actually be possible to show in your display. And here are some already prepared examples. For example, if you take some photo of reality, then it may happen that total contrast is much lower, but because your eyes directly seeing this light from reality still thinks it's okay, because your dynamic range of eyes is much better than for printed material. But if you would put it on display, then of course it would look bleak, because display cannot show everything in this possible range as in reality. So you can make it contrast much bigger, because then it looks much better on this limited range of possibilities what your device actually may show. And so all these digital filters work in such a way that you analyze all entire image, and then you non-linearly change color to some of these pixels according to different kind of filtering. Also, what you can do is, for example, remove noise. For example, here we see some noise here. We can do, for example, change how it looks regarding to the noise. Of course, now it is with so large contrast, it doesn't look right. So we can start here. And then we can check, for example, can we remove these random pixels with different colors in different kind of ways. And then you can do different kind of pseudo colors, for example, to see different kind of differences in this picture better than it was in actual life. You can replace some similarly looking colors to completely different colors, for example, to force differences and see them much better. Here, what is difference so called hue, and hue is balance of white or balance of black, or where is maximum intensity of different kind of colors. And if maximal intensity of color, for example, here is somewhere in the red area, then our eye do not see all small details on this particular picture. But if we shift it from red till to blue, we see much more details here, what we usually don't see in our particular displays and devices. And similarly, as we have problem seeing blue light, our blue light sensitivity is not so high as, for example, for red and green. Actually, for different kind of displays, also blue light is a little bit harder to make because it needs more electricity. You should remember that blue light is more energetic than red light, so generating red light is more efficient for light emitting diodes than generating blue light, so it takes more power and more energy to emit. And because of that, sometimes you have not equal number of red, green and blue dots in your devices. You may have twice as more blue dots than red and green dots in your particular device. And then you can do different kind of local filtering. You can sharpen something, that means increase difference in border section of image. Blurring means decrease differences between sections of different areas. You can detect lines and increase them, apply different kind of noise filters, etc. For example, here what is done is that differences between different kind of areas are increased as much as possible and everything else is decreased, so you see different kind of borderlines much better than it is actually in real life. And then you can do different kind of noise reduction techniques. I usually, when I need to handle different kind of pictures for web and computers in general to see on display, what I do is I decrease resolution to much smaller resolution than it was originally. For example, idea is following that if you have any modern device, even mobile phone as your camera, usually it has very many megapixels here, let's say 4000 pixels in this direction and 3000 pixels in that direction, and that is, if I'm not mistaken, 12 megapixels in total. And aspect ratio actually should be something like this, not that. And then you have these noisy pixels that if you look on particular pixel, or all of these neighbor pixels are actually with different color because of noise. But my particular display is, I don't remember, but I can check. So this resolution, 1920 by 1080, and it is entire screen, not only part of it. So that means that in most of cases I can't see actual resolution for this image taken by my mobile phone. And the easiest way to remove noise is to make it, let's say, 3 times smaller, something like, let's say, 1024 by 700 blah blah blah, which is good enough for web purpose, etc. And that means that several pictures in neighbor picture will be averaged and weighted out, so your resolution for picture will be much smaller, but color representation will be much better, because several pictures will be put as one, several pixels will be put together as averaged into this one single pixel, and its average color will be much closer to truth than these many pixels with random noise for them. But if you need to print them out, for example in large values, then of course you may need to do averaging between pixels with the same resolution as you had it initially. And then what you also can do is you can do another compression of, so this is about lossless compression. When you take one particular kind of image, what is happening is that not all possible colors what you can describe with these numbers are actually happening in this image. And that means you can pick out only one particular subset of all these colors, and then you can describe this subset of colors with more precision than all possible ones. So this is what is called color indexing. So you say which kind of colors you will actually be using from all possible palette here, and then you use only these particular images or these particular places. And now another part about pictures is about raster and vector graphics. So far I told you how you can take images of reality, convert them into numbers and files and represent them on paper or display or whatever. Problem is that you always lose some precision, because you cannot get better image than you originally took in terms of sampling rate, that is in terms of pixels in one direction and another, and in terms of color, how you describe each particular pixel in this color. But you can do it with infinite amount of precision if you do not describe it as a number, but you describe it as an instruction to generate one particular color and one particular shape. And these instructions are so-called vector graphics. Vector graphics are like simple formulas, or not so simple formulas, which describes how you need to draw different kind of lines, curves, how you need to fill different areas, etc. And of course, vector graphic is used for different kind of two-dimensional, three-dimensional modeling, etc. And leading standard as a open standard which everybody can use today is SVG format coming from Scalable Vector Graphic. In general, this is XML file. An XML file is text file with particular markup inside it, so it says what kind of shape you need to draw, what kind of border it has, what kind of fill it has in this area, and then you describe everything as shapes. What kind of shapes do you have? First, you may have different kind of numbers, which, for example, describes color. And you say, for example, fill everything here with color 333, blah, blah, blah. Then you have different kind of lines or vectors, and also curves, if these are not precise lines or straight lines, but are curved, and areas and points. So scalars is just a number which describes something. In most of cases it's either point in your plane or, for example, number of representing color, and then you may say please draw line from this point to that point. That would be vector. A vector of course has direction. For one particular lane you don't need direction for it, but you may need direction, for example, if you need to approximate some kind of curve using different kind of vectors I will show you later. And then you describe everything with this two-dimensional space as different kind of formulas. You can do them in different way. And then if you put them together like several lines together, which makes a closed area, then of course you also describe some area and you can fill it with some particular color. And it may have or may not have borderline here, so borderline may be either infinitely thin or with some kind of weight here and with some kind of color. And vectors are used here, for example, when you need to describe different kind of curves, depending on how you smoothly change curve to curve. So here you will need to use vectors, because vector is going from here to here, and vector is going to here, and you gradually change direction of produced curve from that direction to that direction. And everybody who has used some graphical editor with this object-oriented or vector graphic, then probably you have seen how these editors are dealing with these curves between different kind of vectors. And so good thing about vector is that you can always scale them up and scale them down, and they will always be with the same precision, because you always need just to calculate the same formula for larger and larger area. And so finally about different kind of file formats. There are proprietary file formats for particular kind of editors, like for Adobe Photoshop, for pixelated bitmapped images, and for Adobe Illustrator for these vector graphics. But my recommendation is, especially when you need to communicate with other partners, is to use standardized, in many cases also open formats. Open format in this case means that you don't need to pay any royalty to developer, like patent or whatever, to developer of this format of file, so you can use it for free. And for these raster graphics or pixelated images, the most widely used image is PNG from Portable Network Graphic, which is improved GIF format, which also allows transparency for it and objects with sharp edges. So because it has sharp edges because it is compressing these images, but similarly to lossless sound compression, PNG is lossless image compression. And then you can use JPG or JPEG as loosely compressed image. So here you usually use it for pictures coming from your photo camera or phone, because it allows you to describe much more precise gradients of different shades of colors and grays in these images. And because in nature you have these gradual changes in intensity and color, so this particular compression format is better. What is not so good is that it's lossy compression, and if you will go in details you will see that first it loses some information. It describes color not for all pixels in image, but only for some part of them. And then when it does compression, it can't describe sharp images because it uses a fractal approximation of edges. For example, in PNG, you can very easily describe border between black thing and white thing. But for JPEG, what is happening is that it describes it as a fractal approximation. Here you will see always some decreasing amount of black pixels in this white part and some decreasing amount of white pixels into black part. This is because how it describes changes from pixel to pixel here. And if this compression is very high, you can actually see that these lines are blurred out with like a random noise, but this random noise is actually not random. It comes from this compression algorithm, how it describes changes from color to color. So, and then you can use GIF as an older format for PNG. Only good thing about GIF is that it also has standardized way to contain animations inside images, what actually means that you have put many images into the same file and you describe how frequently this image should be changed to that image. And then there are files like BMP and TIFF which are uncompressed. So you use it only if you, for some reason, need to save all initial primary values for all your pixels, because it is uncompressed like a WAV file. BMP for image is like WAV file for sound. So each particular pixel has its own value written into this array of numbers. But TIFF is either uncompressed or compressed without losing anything, so it may be a little bit smaller in size because of that. What is not so good is that because of historical development, TIFF format for Microsoft Windows users is different than TIFF format for Mac users. So you may have some kind of issues if your particular editor, your particular program do not know about these differences. And then about vector graphics. If you do not look into proprietary formats, how you save these, like in CorelDRAW, in Adobe Illustrator and other things, then leading standard is SVG. So it's just text document which describes all these shapes as numbers, What is not so good about this text document that for complicated graphics it may be very large, therefore you can compress it with lossless compression using gzip as a compression format, and you may save it as a svgz format. So it is just gzip compressed svg file. And then some of more proprietary formats still may be widely used. Windows Meta format for Windows applications, PICT for Mac applications, and EPS for PostScript extensions for old school printers and software for different kind of printed materials. Neither of these should be widely used. If your editor supports SVG or SVGZ, you should use that format because then you have less problems porting it to something else. But if you are forced to work with more proprietary formats, then of course you still may use these particular formats as well. And that, I think, is it about imaging. Do you have any questions or comments so far? Okay, then about your homework or practical exercise. Practical exercise is number 5, short name imaging. And the first thing you need to download this zip archive. And then probably we need to extract it. And here we have different kind of GPG files. We can open it with different things. One is Risetto Image Viewer. And here it says it's summer, somewhere, then winter, somewhere, autumn, somewhere, library, and spring. So that's what is given to you. What you have to do with this? You have to prove your editing skills with bitmap files or these raster files, or call them whatever, that you can put yourself in some of these places using these as a background images. And for me, I think I found some place already. Okay, so somewhere here is some older photo of me in summer, but I don't like it, not because I don't like myself, but it has too many details here. And maybe for demonstration purposes I will try to use this image because it has much less details to deal with, and maybe it will work out. And because it is in winter, probably I will use which file? Okay, this winter file as a background. So you can use any editor you like and you know, but when talk is about different kind of these rasterized bitmap images, there are bunch of different kind of editors. I myself, I'm using 3 different ones. For simple cut borders draw something particularly for Xubuntu, I'm using an editor called Color Paint, not with C but with K, because there are many of applications which are written with KDE graphical libraries as a backend for them, and there are many Linux-based operating system distributions which uses this KDE as their main framework for graphical libraries and graphical interfaces. Probably most famous one would be Kubuntu with K, not C, and Linux Mint or whatever. So I'm using Xubuntu using this LXDE graphical manager because it's faster, but here I use this editor just for simple drawing and cutting things. So it is very similar to Microsoft Paint. So if you need something open quickly and do something quickly, this is not bad editor to have. Other editor I have particularly for freehand drawing is this editor. And what is good about it, it has seemingly infinite canva, or this place where you can draw, and it has better representation of different kind of inks and paints, etc. So this editor is called MyPaint, and I mostly use it for these illustrations written by hand because it shows better pictures than, for example, Color Paint. It is, for example, if I take like so, this actually I could use this as well, but the problem here is that it always has preset maximum size for image, and if I run out of it I need to clean everything or whatever. But in this editor I can just move it to other thing and continue, and then I can move back if I like. But for serious editing, of course, de facto standard for open source world is GIMP from GNU Image Manipulation Program. And of course, because of this political correctness, etc., some wanted to rebrand it to something else, because if you search for GIMP, it shows for me this one, but okay, let's open private mode. This costume and mask is GIMP as well, at least in English. But fortunately here initial developers won that of course English is very important as a language for entire world, but so it's still called GIMP, coming from GNU Image Manipulation Program. And so then if I chose one of these images, where it was, I will open it with this GNU Image Manipulation Program. And I'm not super user of a GIMP, so some of you may actually know how to use it better than me. But what's important here is that it allows you to work with layers. These layers initially are transparent, so if you write something here, you see that original background is actually not changed, but only some changes here are coming from these things. And then I also need to open it in another file, and I need to cut it out. If that would be... Oh, this works pretty well. So, see difference here, that here this auto selection tool works pretty good, because everything is just mostly black. But if I take some harder to use picture, and you see here that here are much more different kind of colors, I can't select it very easily. Maybe you can, for example, select everything else and then delete that part, and then select that thing. So it takes time. Then you need to use such tool like this tool, and put some shape around it with some precision. And that of course takes much more processing and manual. So putting that in front, is a little bit harder. So, because of that I will actually, even though it's nicer picture, it's just harder to manipulate. And here I need to take my face as well, so that may be a problem. What happens if I try to select that one? And here we can do it something like this. Select some image. And of course you see that now it doesn't look realistic at all. So one of things what will be rated is that why it was not selected. Let's assign it. And then probably what we may do here is that here we can, again, I told you, in most of cases I'm not using brightness and contrast for these pictures because I actually like to use these curves. As a more dynamic way to adjust the colors. So curves here, let's make everything what is bright brighter, everything what is dark darker. And so we need some adjustments here as well. Let's make here face brighter. Maybe just and now it still doesn't look realistic. What can we do is let's make myself standing in snow. Maybe not in that way. And I don't know, maybe we need to add also, so I'm switching to background shade. What can we do? Let's make some shade here. Vice versa. This is not. Okay, something like this. So then you make it nicer and more realistic. And here, of course, you can save it as a internal format for particular editor, and when you need to have all these internal details like layers and different kind of pictures inside these layers, then of course you save it as internal project format for particular editor, like for Photoshop that would be Photoshop project. But what is required is that you export it just as a JPG image with resolution here quite small. So if we look here on properties here, where do we see? Here we have much more pixels as we need in resolution, and you see here that they are quite noisy. And one of the things we can just remove noise here with filters. And not in this layer, but here. nothing changed. Let's make it. And yeah, I needed bigger one. And then you are not reducing total resolution, but you remove noisiness of these things. But what I usually do if I need to convert different pictures for computers, I just resize it to smaller one, and of course it averages all these noisy pixels automatically, because it averages several pixels from original image to 1 pixel into a smaller image. So, and I need to export these I1 GPG. And here we can change many different things if we like. These are not checked, so it's up to you. I will just accept defaults here. And here are, for example, this compression, how many of different kind of colors you are using for these particular pixels. I do not know all this meaning here, but it says, for example, what is mask for pixels for different kind of colors. So here all pixels will also have color information added to them. Here some of these colors will be ignored, it will be just grayscale. But I agree with defaults. Yeah, and if I open it with some image viewer, some artifact here. So this is let's say quality of image will be accepted as a passed. So you will not get 10 out of 10, but you will get like 7 out or 8 out of 10 for this particular activity. Any questions, comments on this exercise? Are rules understood and everything else? Okay, one told yes, and I hope that he or she represents majority of class. And yeah, if I decided to save this project, I save this, I do not save that. So that's about editors for pixelated images. Other part is to deal with vector graphics. And I was struggling a little bit to decide what exactly I should ask from you that you still can express your individuality and your drawing skills, but can be easily checked. So what I decided maybe is not the most widely used thing what you use for these vectorized images, because for vectorized images, again, there are different kind of editors, and one editor which you can use is LibreOffice Draw if you are using a LibreOffice Office suite, or Microsoft, how it's called, if you use Microsoft Office. And good thing about this tool is, I do not know where it's located in the menu. Good thing about such editor is that you don't need to install anything else. You can draw different kind of images. You can save it as an open document format image and other things. And you can also export it, for example, to SVG. As this international standard for scalable vector graphic. But it is pretty weak as an editor, so usually you use it only if you need to make some very simple graphs there. And de facto standard in open source world, what in proprietary world would be this Adobe Illustrator, is editor called Inkscape. So it's not installed by default in Linux distributions because it takes a little bit more space in disk and much more complicated, but it is more powerful. And again, you may save it in different formats. One format is scalable vector graphics. Again, it supports many layers, how you can put objects in front of objects. And I'm not power user of this editor. I use it only occasionally because my needs for graphic processing is not too complicated. But to prove that you can deal with this and that you can't just steal some copy of the internet. So plagiarism here is the hardest part, that you may just take some very complicated Inkscape image and take as your own. Therefore you have to use required input. And required input is, where it is this file, library GPG, and we can immediately open it with Inkspace and import. And here I will again agree with defaults because I don't know how can I improve it. So this required input is just because with that required input you can't just take any picture from the internet. And again, you need to put yourself on this image, but this image should be saved not as a pixels but as objects. And particularly for Inkscape, converting pixelated image into objects is very easy. As I right click here, or in general it is about path. You describe anything as a path, and here I think there was some requirements. You should have at least 16 different colors. So you put 16 colors here. You use colors. And here, depending on how many attempts and iterations you have, you will have better and better approximation of this pixelated bitmap image into objects. But each of these scans and attempts takes time, so I will not. You are not required. So what is required is that you convert this picture into objects. And of course, in worst case scenario, you can just use this image, I think I did it, as a background and just draw on top of it by hand. Like choose some of, and just draw this image by yourself. But that of course will take a little bit more time. And when you have converted it, what is important here is that even though here in pass it has remove background, I do not know what exactly it does, but what I expected was that this original bitmap background is actually removed, but it is not. So it puts your object-oriented image, and you can see that these are just different kind of shapes by selecting it with drawing tool or shape editing tool, but this background image is still there. And if we export it as a scalable vector graphic, what was my identifier? There it is, here it is. What is happening here is that it is still quite large, so with 1 megabyte of data, and because it is just XML file, we can open it with any text editor, like Mousepad. We see here that here is actually base 64 encoded bitmap image still included, and that's what makes this picture very hard. But here are coordinates of actual shapes here, what we converted. So therefore what you need to remember is to delete this background image after that. Put it here, and then I was careful enough, I actually saved this GIMP project. Where is this GIMP project? Oh. Okay, let's open GIMP and look. Recently used projects here. So I will copy and paste this image from one editor to another. And here again I need to convert it into objects from bitmap image. Maybe background is only this white part here in screen, not the entire image. Here. And again I need to remember that here Underneath it is original bitmap image still in that picture. And then I think I didn't do everything. I had to add my identifier in these files as well. So I was not careful enough. There are too many opened windows. So here I also need to, where are text is here. Maybe let's make it a little bit bigger. And here again, I think we talked about fonts when I mentioned operating system. Font is bunch of data which describes how to make shape for a particular character using these different kind of formulas. But if I put it as a actual font here, what is needed is that everybody who will try to look on this image will also need this sans-serif fonts to see this text properly, because then this image will be described as a font somewhere. So, and if some of viewers will not have this particular font installed on their operating system, they will be falled back to some different font size, so it will maybe look different or even wrong. And therefore, to make it absolutely independent on different things, this part of image again should be converted just to bunch of shapes. Again we go to pass, and no, not bitcard or bitmap image to pass, but object to pass. And now if I save it as scalable SVG, I think that there will not be anything mentioned about fonts in this picture at all. Well, still is. Why? And we can always check that, no, it shouldn't be font. And again, and this is the only thing we have. Okay, but that will not be checked. What will be checked is size of your image, and that your size is not too big because you forget to remove actual bitmap image from this. And now, when it's done, we actually need to check that it's A for landscape, this one, A for landscape. Now save or apply, hopefully it has changed. And we see that the original image was with different aspect ratios on A4. Okay, we will just fill up this A4 in following way, because I think stretching it, actually it doesn't look too bad if I just stretch it to these borders. it saves it as a native SVG file already. So that is second part, and first part was actually not completely done. In this GIMP image we also had to add our unique identifier. Let's put it in front as well. Even bigger. Too big. And it's not visible. Let's change it to what? And for fonts it's different part, for color, okay. And I need to export it again. Such picture, let's double check. So I think this looks passable to me, and SVG, if you open it just with a viewer, you can open it with like any web browser. And this also looks possible to me. And we can check, for example, that F4 here to open in current folder. Check properties of the GPNG file. Oh, forgot to make it smaller. So and now this is correct size. And what we need to check about this scalable vector graphic. No specific requirements. Then, if it looks correct, to you. That's interesting. Let's open these with something else. And something else could be where is LibreOffice? Looks more or less okay into LibreOffice editor as well. So that's about second part, and then of course you upload them here with just a reminder. So one is JPG file, and another is SVG file. And that's it. Any questions or comments on that?